All right, I don't know exactly what's going to happen here, but we'll just take our chances because, I can do another take if it blows up. So, all right, I'm running Kimi K3 and I'm running WAN2 on the same laptop concurrently using Psilon. So Psilon is a GPU operating system, if you will. It handles all the virtual memory and process organization that, like a Windows or Linux OS handles for scheduling applications running on a CPU, except that Psilon does it for AI models, frankly, any Python application, really, on a GPU. So even though this laptop, as you can see, only has 24 gigabytes of RAM and 128 gigabytes of video RAM, I can run two models that require on the order of over a terabyte of VRAM in this tiny 24 gigabyte window because Psilon's handling all the memory management for it. So today I wanted to just do a brief overview of what Psilon is supposed to be for everybody and maybe contrast it a little bit like something like Llama or vLLM. First off, to understand what problem am I solving? So the idea is that I want to democratize the ability to use modern AI models, including the really cool frontier grade ones, for everybody on whatever computer they have. So as we all know, most of the AI ecosystem is heavily tied to NVIDIA and CUDA. And so one of the first things we did with Psilon is generate a whole bunch of additional backends. So here you can see that we have a Vulkan, a CUDA, a DX12, and a web GPU backend. Now, why did I choose those backends, and why are they so Windows-centric? It's because we're trying to make this for consumers, not for us nerds and Linux heads and Mac heads. Not that a Mac head can't be a nerd, mind you. For the vast majority of consumers who have gaming computers and laptops that are perfectly good AI boxes or devices, if you could just make the AI work on them well. So Psilon's designed to democratize artificial intelligence by enabling any kind of AI, unquantized, unlimited, to run on whatever hardware you have. That's the intention. And as you can see, look at it light up. It's working. So here you see the GPU memory is maxed out. The 5090 GPU is totally saturated. There goes my NVMe drive. Look at it. It's just getting loaded because we're paging VRAM through the CPU and cold paging to the NVMe drive. And there's my CPU memory. Ironically, it's working hard, but it's clearing out to the NVMe drive. It's got to free up some CPU memory because we are really killing the GPU. And here's the amazing thing. That GPU is running at damn near 100% occupancy. So even though I'm massively I/O bound, Psilon running two frontier AI models concurrently is doing a great job of keeping that GPU jammed. How is it doing that? Well, there's several layers of technology here. First of all, there's memory virtualization. We are running caching layer out of the GPU. So we're caching VRAM. We're hiding from Python the actual limitations of memory available from the AI. And so that was one of the battles I've been having over the last few days, is fooling Python when it runs these AI models into thinking it's got unlimited amounts of VRAM and getting all you don't have a big enough GPU to run this model, or I'm going to GIMP the AI because I don't think you can run all of the experts simultaneously. So I made all that go away. Now both of these AIs think they've got their 2 terabytes of VRAM. They don't know that they're running totally virtualized. Second, you got to get them sharing the GPU, and this is the big trick. Believe me, I'm far from having it perfectly here, but the fact that it's working at all is a miracle. So you can see that Kimi K3, I've asked it how many moons does Pluto have, and it's still in pre-filling. And that pre-fill phase is probably part of what's really jamming the NVMe drive. And then, of course, WAN 2.2 here is rendering my render a realistic video of Pluto with its 5 moons orbiting it. No idea what I'm going to get here, but you can see it's gotten started. So both of them are getting the GPU. I've got Cursor watching all the analytics in the background, so as I do this demo, it's looking for paging, thrashing, that kind of thing, and then I'll analyze it and tune it better. But right now, it's working. It's sharing the GPU with these two AI models. So again, how does it do that? One, it's paging. Paging memory in and out. That's an easy one. Its operating systems do that. Secondly, probably the big thing that Psilon does that no other runtime that I'm aware of does is it's streaming the AI model through the GPU. So it's chopping, Kimi K3 is something like 92 or 93 layers, and it's passing one layer through the GPU at a time and hanging on to the attention data that comes out of each one. It's keeping that on the GPU, but it's paging the layers in and out as it goes. And that is, and you would think that it would be very hard to keep the GPU occupied like this doing that, but we're succeeding, which frankly, I'm just as surprised as any of you are. I'd love to say I did this on purpose, which I did. I just didn't think it would actually work this well without a lot of additional work. But for some reason, we are getting very good occupancy. And to be fair, I don't get occupancy like this when I'm running one AI model at a time. So one of the weird features of running two AI models at the same time, neither of which has enough VRAM, seems to be maintaining high GPU occupancy somehow. We're going to figure out that later. But why is it plausible that it's doing that? Well, first off, I'm using direct storage on Windows, which is very fast DMA NVMe transfers to the NVMe drive. So I can hit those NVMe drives at around 12 gigabytes a second into the GPU, which sounds incredibly fast, but actually I should need about 20 times that. However, these models are so computational heavy that my 5090 state-of-the-art laptop GPUs kept pretty busy, apparently, running each one. And the spikes you're seeing, each of those dips there going on the CPU, or on the GPU rather, that's the layers being streamed in and out of GPU memory into CPU memory, and they're being paged in and out. So that's what's happening there. That's what each of those dips are. So you go, hey, I'm not getting 100% occupancy, but that GPU is pretty darn busy right now. Let me see if I can. There we go. Now you can see. You see it's working here. There it is denoising. I got my first denoising step, so maybe we'll start seeing Pluto here pretty soon. And then over here on Kimi K3, still pre-filling. And I gave it a 65,000 token max token window. I just said, go ahead and write, War and Peace if you feel like it. All right, so we're paging memory, just like an operating system does. We're also streaming the two models through simultaneously, but both of these models may have layers plus attention values that are even bigger than 24 gig. They don't, but they could. So we're also doing what's called tensor striping, which is we're slicing the layers up into little slices and feeding them through serially. Now, in this particular demo, both of these giant frontier models have a lot of layers, but each layer isn't that thick. It's not so heavy that they can't coexist on the GPU. So the tensor striping isn't really kicking in. In this particular case, I think that we might get better sharing, that is, each one gets more cycles if I forced tensor splitting on these, but it's not necessary in this case. So this is not a great demonstration of the tensor splitting going on here. However, over on Thanos, the machine I have on the other side of me here that has two big GPUs, we're going to demonstrate, we're going to try running two models on that and see how the Psilon caching architecture ends up splitting work between two GPUs on a machine that has a 1/4 terabyte of CPU RAM and 48 gigabytes of VRAM divided between two R6000 workstation grade GPUs. So that may be one of my next demos here. We're streaming, we're caching. Tensor striping is really for distributed computing. We're not using it that way. We're actually using it for time slicing, so more like an operating system's process scheduler. But on a multi-GPU system, Psilon will use it for distributed computing of layers as well. And so all of those three architectures combined makes it possible to run a frontier model unquantized, uncompromised on this laptop. Now, that isn't to say that we wouldn't maybe like more speed out of it and might be willing to make some trade-offs in model quality for performance. But one of the things I'm going to do in Psilon is give the user complete visibility and control over that. So Llama does handle some level of caching to the VRAM, but it still tries to jam the whole model entirety into VRAM, and it does that by massively quantizing it, which frankly badly damages or breaks most models. And then Llama isn't aware. It's not in touch with the Python runtime that generated the model. So when you run a Llama model, the user kind of has to hand tune the model to run in their particular environment, and you have to hand quantize it. And you don't know how much damage has been done to the model by quantizing it. You just know it's not as smart as it was supposed to be. So Psilon, the idea is to not involve any hand tuning at all, to just always generate optimal runtime, to stream so that you don't have to compromise the model to fit it in VRAM. And second, if we do quantize the model, we're going to give the user dials to tell exactly at runtime how much the model's accuracy or how much of its reliability is being compromised by adaptive real-time quantization. So we're going to go from kind of a primitive environment where you have to hand tune everything and hand test it without kind of analytical control to run a model in Llama, to you can just run any frontier grade model untuned. Psilon's going to make it work. And if you're going to compromise the model by quantizing it, you have mathematical, numerical control over exactly what's happening without having to guess or experiment with it. So that's the major difference between Psilon and something like Llama. Now, VLAN's meant more for enterprise kind of grade deployments in the cloud, and it handles the more advanced kernel fusing and scheduling. And Psilon could do that too, but weirdly, it's not our first priority, because all these CUDA backends that I'm running here, or I mean all these GPU backends that I'm running here, I'm going to optimize them. They're hopefully going to be very fast, but it doesn't actually matter because I'm I/O bound. So it's the getting so much information in and out of CPU memory and NVMe memory into the GPU is Psilon's first job, and that's I/O bound one. So that extra, if the calculation on the GPU is a little slower, it really doesn't matter because it's waiting for the NVMe drive or CPU memory to page anyway. So ironically, being the fastest algorithms and the fused batch efficiency that you're getting from something like vLLM is not the first priority for Psilon. Now, I do have highly optimized fused and batched backends coming for Psilon, but I suspect they won't change the numbers much. What I suspect will have a bigger impact on tokens per second for running these frontier models will be the adaptive quantization that I plan to add a little later. So, punchline is, this is meant to be a much more advanced consumer media player for AI. So think of it as trying to handle artificial intelligence the same way we handle streaming movies, to preserve the maximum quality and full precision of the movie experience without the user ever noticing it, and definitely without the user having to hand tune their streaming parameters for their particular compute and network environment. You want your streaming media player to just handle that, and that's what Psilon is essentially a streaming media player for artificial intelligence. I just want the models to work out of the box without regard to what my limited hardware is capable of, and I don't want to have to run a science experiment and spend hours hand tuning things to try to get the best possible behavior. I just want to play with the AI. That's what I just want to interact with the AI. I don't want to deal with this stuff. So that's what Psilon's endeavoring to do here. Let me see how our look at that. Pluto's moons are coming up. There, you're starting to see some of the first images appear. Kimi K is still pre-filling. So, I'm hoping that's not jammed. I'm hoping it's getting all the GPU cycles it needs and that pre-filling is just slow, but I'll have a chat with the AI on the background about doing that. But that's essentially an overview of what Psilon is think of it as a media player, a consumer media player for frontier grade artificial intelligence. And if you can't afford a fleet of GPUs and really expensive NVRAM, well, cheap consumer NVMe drives appear to work quite well at keeping a consumer GPU fully saturated, and that's what Psilon's designed to do a great job of. Take care, and I'll see you in the next episode. Open Broadcast Studio.